Now we will move on to the series RLC circuits, which are a combination of both RL and RC circuits. You can have the characteristics of both RL and RC circuits by adjusting the inductance and capacitance. You can have whether an inductive based circuit or a capacitive based circuit. You can get simultaneously the characteristics, either inductive or capacitive, or if you balance them both, you can get a resistive characteristic also. So let's get back to the basic information. Now this is here sinusoidal AC voltage which I am applying to a series RLC circuits. Now the impedance, each of these elements of a different type of opposition to the flow of current, right? It is given by R, it is given by JXL, it is given by minus JXL, isn't it? Where XL is equal to omega L, XC is equal to 1 by omega C. Now the total impedance which is offered by the three elements is given by, so this is resistance, this is inductance, this is capacitance, right? So this is R, this is JXL, this is minus JXL. If I join these things and if I take J as common in these two elements, I'll get Z is equal to R plus J into XL minus XC. This is here Z, isn't it? Now, if XC is low, then XL is high, which means your circuit behaves as an inductive circuit. If XC is high, then automatically it behaves as a capacitive characteristics. It shows you capacitive characteristics. Now when both are equal, they cancel out each other and you can get a resistive characteristic from your circuit. So this is the advantage of having RLC combination. Okay. Now this, if I substitute XL value, which is nothing but omega L, XC, which is nothing but 1 by omega C. So this is my representation in terms of rectangular form for an impedance. Now what is the polar representation of this impedance now? See, Z is equal to R plus J. This is entire is the imaginary formats. Okay. Now if I want only the magnitude of this one, so what I should do, it is square root of R square plus XL minus XC whole square. Isn't it? Now what is the phase angle of this one? Is equal to tan inverse of XL minus XC. This is the entire imaginary part by R. Okay, this is the magnitude. This is my angle. Okay, magnitude and angle. This is how your impedance is represented in rectangular and also in polar formats. Now, if you move on to the currents, then your current is given by, I is given by small v by z, where v is in sinusoidal equation, where z is it is in rectangular format. If I convert these two into polar format, this is the equation which we have seen in the previous sections also. Now here, in this case, what is magnitude of z? It is square root of R square plus omega L minus 1 by omega C, isn't it? Now, what is the phasor diagram for this one? See, as already I said, you do have three elements, and the combination of these three is VR, VL and VC. If I take current as the phasor, okay, now this is VR, this is VL, whereas this is VC. Depending upon the magnitudes of VL and VC, you will be taking VL minus VC, isn't it? If VC is higher, then automatically this will be getting cancelled out and you will be getting somewhere a value like here. Right. Let us suppose if this is higher, then automatically you will be getting a value, resultant voltage will be like this. If both are equal, then you will be getting an equal voltage here Vs. So it all depends upon the value of your inductor and capacitor, the phasor diagram. Okay. So see, the capacitor reactance will be lagging the resistance by 90, whereas inductor reactance will be leading the resistance by 90 degrees. So that's why if you do have, see the cos phi also, which is nothing but cos of tan inverse of XL minus XC by R, isn't it? Right. So if XL is higher, then automatically see, if I draw the figure of AC sinusoidal, if XL value is higher, if XL is greater than XC, then automatically my current will be, which means that it will be lagging. If let us suppose XC is greater, then my current will be starting like this. So this is for XL is less than XC. Now this is for XL is equal to XC. My current will be exactly starting just like your voltage signal. So see, the power factor is going to vary if I vary the values of RL and C. It all depends upon your magnitudes of L and C, literally speaking. That's why I write it here. If XL is greater than XC, then your current lags voltage. So the power factor will be between 0 to 1 and it will be lagging. If XL is greater than XC, if XL is less than XC, then current leads V. So your power factor will be again between 0 to 1, but it will be leading. It will be considered as leading. Now, if your XL is equal to XC, if XL is equal to XC, see what will happen? It will become 0. This will become 0. Tan inverse of 0 is 0. Cos 0 is 1. So your currents will be in phase with I. Your current will be in phase with V. And your power factor will be absolutely 1, which we call it as unity power factor. We call it as unity power factor. Okay, this is what happens when you XL and XC vary with respect to R. Okay, try to remember this slide. I'll be asking for 1 mark questions in your examinations. Okay, now this is the representation. Now, depending upon your XL and XC, you can have the impedance triangle. Okay, this is R, this is XL, this is XC. Right. XL and XC, they get cancelled out. You will get somewhere around Z. This is in case of XC is greater than XL. Let us suppose if your XL is greater than, then it can be Z. If both get cancelled out, then this can be Z. So this Z, it will be varying either this side or to this side. Okay. So I hope that now you have understood how to draw the phasor diagrams and what happens when your AC supply is given to your series RLC circuits. Okay, how the current will be varying and how the power factor will be varying. That's all we have seen. So, as already mentioned, these are widely used RLC and RLC circuits. You should learn their characteristics. Why? Because they can be used in amplifiers, your communication systems, particularly in filtering circuits and processing of your signal. Oscillator circuits also are communication circuits. In amplifiers means current amplifiers, voltage amplifiers are also there. And for tuning, these are also, they come under filtering circuits. And these also, they come under radio signals. Okay. So in communication and electronics, particularly to control the V, I and F, in one way or the other means, you do require these signals. And that's why you should be able to understand their characteristics. I hope that now you are able to describe the response of these circuits when they are excited by single phase AC supply. Okay. So I hope that now you will be able to derive the expression for power factor in a series RLC circuit. You give me a detailed analysis how it will be varying and what is its minimum and maximum values and what are the different zones. I have told you for XL is equal to greater than XC, what will happen? For XL is less than XC, what will happen? And for XL is equal to XC, what will happen? How the power factor will be varying. You explain me in your notes. Okay. And prepare well and come to the class. Thank you.